Hello, everybody. I'm Mark Madsen. I have been doing data stuff for about 30 years now. And I started as a programmer, moved into operations. I've done pretty much every job in IT. I have been, a CIO and a CTO. I've been a developer. I've been a DBA. I've been a janitor in a data center, which is, in fact, how I learned about mainframe programming. Janitors have a lot of free time. It's a good job if you're in IT. So I'm going to talk just about some analogies. Now, one of the things about analogies in the big data market is that they're all wrong. Um, and the thing is, if you use a bad analogy to explain something to somebody else, then you frame the problem incorrectly, and then you think about the problem incorrectly. And so part of what I want to attack in this talk is just some ways of thinking about problems a little bit differently. As an example, the horseless carriage. The horseless carriage is how people talked about cars for many years. And the problem is that when you think about it as a horseless carriage, you think about it as a carriage. And if you look at one of these early horseless carriages, this is not the earliest, but it's the best picture I have. It's a carriage with carriage steering and carriage brakes and everything else and an engine strapped to it. The one before this one, the carriage was pulled by a motor on four wheels harnessed to the carriage. So people were thinking about it exactly as a carriage problem, not thinking, here's the technology, what is the capability that I want, and how can I use the technology to give me that capability, which was driving a car. Likewise, in the big data world, we have terrible analogies. Data lake is a great example. I hate the marketing around data lake. Lakes occur in nature. You don't make lakes, they just exist. And a lake is full of what? Water. It's full of undifferentiated stuff. So a data lake is just a place with a bunch of bits in it, but you can't tell one set of bits from another set of bits. But it's important to be able to categorize and sort and differentiate data. And so when you start thinking about the data lake, you start thinking about just dumping the data in. Don't worry about it. Or as Devlin would call it, a data reservoir, right? You at least have the engineering to build a dam after which all of the data piles up behind it and floods all of the infrastructure, drowning everything that's inside. And when I first started doing data-oriented systems, like big data systems back in the 90s, which would have been machine learning for fraud detection and things like that, or just basic data warehousing, business intelligence. Of course, back then, big meant, 50 gigabytes, but it was the same problem. The whole idea there was early on, just back up all of your databases into this one big database, and you have a big pile of data, and you ended up with a data junkyard. And now you're just going to end up with a polluted data lake. We know this approach, this mental model of how to think about the problem doesn't work. A new one that's different from the past is that today we have more data from many more sources than we did previously. And so people have talked about data exhaust. I think Splunk marketing uses data exhaust as an analogy, which is great if you're thinking about choking on the fumes of the applications that you're running, and you're thinking about data as a byproduct. Data is probably the most important part of your data processing job. Your programs operate on data, and to think about it as exhaust, it's sort of like this cloud of stuff. There's no structure to it, there's no pattern to it, and once it's emitted, you don't think about it anymore. The problem is that data has a life of its own that goes on for a long time. And one of the final analogies is data is the new oil. Right? Looking at the economic aspects of it, they say, well, it's a resource and you can process it into many different forms and make money off of it doing this or run your business better doing that. And that's actually not a bad analogy. It works. It also works in the sense that there are data spills, privacy leaks, people privateer with data, they take it hostage and blackmail you with it. So it fits for both models. But the real thing about data is that it's a choice. It's your choice when you write an application. When you write an application, you have data structures. You structure the data in your code, and then you're using persistence layers of one sort or another to store and use that data. And what you choose to record and what you choose to process is what's important. What you choose to measure in an application, what you choose to log or not log is important. I just sat in on the Pinterest case study, and one of the things at the end of his talk was, Pay attention to what you log. Log as much as possible about your operations if you expect to be in a high-scale environment. That is the choice that you're making. And that's the same whether you're building ERP systems or building web-scale sites. So when you look at these analogies, they frame how you think about things. And one of the questions is how we got to some of the places we got. And I'm sort of a computer historian as well as doing geeky, data stuff. And I love some of these old quotes. There are lots of things out there we didn't know existed before. And so one of the things I like to look at is looking at past ways of organizing data. Now, last year I talked about clay tablets and Sumerian information hypercubes and things like that, because they actually invented the multidimensional data model 6,000 years before the patent in 1962. So I'm just going to go back this time to some paper era stuff around, the Elizabethan era, because that's when books really took off. So we're talking 1550 to 1600. And we have commercial printing presses. Printing is now gone wild. Everybody's got paper and books. And the thing that was unique is that instead of personally transcribed copies, printing presses produce exact copies. So now we can have an exact copy of the same thing many times, spread over many places. We solved problems just like data problems today. The data problem of how you serialize objects, for example, do I use Avro, do I use Thrift, do I use some custom XML? It's just like font standardization. The principle there is that you're writing out data that somebody else has to read. Now, when we had Latin texts, there were three different variations, well, there were more than that, but three very common variations of Latin text. One of the texts was for the academics. One of the texts was for the religious scholars. One of the texts was for the non-religious scholar, we won't get into it now, but the philosopher. And the font that you wrote could not be read by the other classes unless they were trained to read that. It's very much like writing data into Hadoop and then having to have an input-output formatter that you have to bind into a program, essentially customizing APIs for everything, or writing out formats that other people can't read. The single aspect of font standardization plays out in the database world in the form of SQL as a least common denominator for describing data sets. Now, during this period, we went from 8 million books to 200 million books. And the population of Europe was much smaller at that time than it is today, obviously. And so one of the things we ended up with was, how do you categorize data? Where do you put this data? Data is recorded into books at that time. So that's the container, the logical container of structure. And in the Elizabethan era, you basically had two choices: sacred, profane. Sacred data, the religious stuff; profane, everything else. And so when you have these books, you just shove them in the library. They're in two things. There's maybe 50 of them. You chain them to the shelves. It's not really a big deal. But when you start to get so many books being produced, you have new problems. So along comes Bacon, not that Bacon, Francis Bacon. And Francis Bacon, of course, he's looking at the way the Vatican did it. He's looking at the classical era. And he reclassifies knowledge. And he says, well, actually, there's three categorizations. Instead of sacred and profane, we're going to have history, poesy, and philosophy. History, in his world, was everything that happened. Poesy was everything that you could imagine could possibly happen, that is, fiction. And philosophy is everything that theoretically or actually can occur. And so he had this division, and he started taxonomy around data and knowledge. So you get into the 17 and 1800s, now we're talking about the Georgian era, natural philosophy, the scientific revolutions, the Enlightenments. And when this happened, everybody was making even more books. The number of books doubles again during this period. And the variety of information in the books, the ability to reproduce these things, creates another explosion. We get into the Victorian era. We're now 300 years on from Francis Bacon. And the information problem of the day is industrial printing. Because industrial printing produces books at such an incredible rate that you no longer have the ability to properly store and manage them. But it's not just books. Now we have newspapers. We have the equivalent of modern-day magazines. We have leafleteers running wild in the streets. And this explosion of specialized knowledge creates the need for more and more taxonomy. which is ways of categorizing and storing information. And levels of indirection. You now have to think not just about a library, you walk in and find the book you're looking for because there's 50 books. There's now 5,000 books in a library. How do you organize the shelves to find those books, and how do you organize the knowledge inside of those books? And these old models had no levels of indirection. So people started paying attention to library science, which brings us into the modern era, essentially, with Melville Dewey. And I'll point out a few things about him which will be relevant later. Dewey came up with the Dewey classification system, which was for a period the most common library classification system on the planet. It's taxonomy. Basically, it's a top-down tree-structured orientation where you navigate down a tree like a bee tree, only not a bee tree, and you get down to a shelf of books, and that's where you land. And he built this to help you get books onto the shelves and for librarians to help you find the books that you needed. He was an efficiency expert, so you'll notice his name. Normally, Melville would be spelled V-I-L-L-E, but he stripped off the L and E and changed his name legally because it was more efficient to strip those two letters off. He was all about operational efficiency. The other person that he was competing with during this era was Charles Cutter. Cutter had the Cutter classification system, which a lot of university libraries still use today. The Cutter system, of course, managing knowledge, not just books. And he designed a system that was not top-down, it was bottom-up, like a faceted classification model. So as you add attributes, you expand the system. It's like the difference between the schema in a relational database and the schema in a sparse table store, something like HBase, where it can be flexible and it can adapt over time, except that in that era, it was all on paper, which made that a lot harder. Now, what this gives you is a bottom-up orientation. It gives you a model of flexible information architecture and lets you identify a single book. See, the thing about the Dewey system is that it's a block-oriented model. People always ask me why I look at library science. It's because it's like a database. A shelf is like a block. The books on the shelves are like records. And the Dewey Decimal System says you can find this book here. And then you have to scan that bookshelf to find that book, which is exactly like how Hadoop works, right? The basic Hadoop model is there's a 64 or 256 megabyte chunk. Now, scan that to find the record that you're interested in. Now, if you use H-files or something, of course, you have Bloom filters and other things on the end of that, but that's more like the Cutter model. The Cutter model says, here's an identifier. It is a unique identifier for this single thing, and it's immutable. If you come up with a new book, a new version of the same book, a book with the same title, it's going to get a different identifier, right? That is essentially saying that there is immutability in the data structures, which gets you a totally different range of behaviors and ease of finding information. But who won? Dewey won. Dewey won because of pragmatism, right? It wasn't that his model was better. In fact, his model was worse for most things. But for the problems of the day and the technologies that he was using, it worked really well. And the technologies are paper card catalogs and paper systems where every time you have to do something, you just scrawl it onto the end, whereas the Cutter system meant having to do the equivalent of like a tree balance. And so it was good enough to get the job done without overworking people on the paper front. The other side of it is far more interesting. He solved the ingest problem. The real problem Dewey solved was that libraries received books faster than librarians could put them onto bookshelves. And so if you can't get a book onto a shelf fast enough, then the books pile up, and eventually they start throwing out books, which is exactly what happened in many big libraries. They could not afford the number of people to put it on. It's like the equivalent of trying to run a website with a database behind it like Oracle that can't scale past the size of that one box because you can't afford it. And so he solved the problem of ingest by making it very efficient to very quickly get shelves on the books on the shelves, because it doesn't matter exactly where that thing goes. It just goes into this bucket. The other thing to pay attention to libraries for is how the librarians themselves shelve books. Interestingly, you'll find that they invented things like the quick sort, the shell sort, the insert sort, but librarians shelving books use adaptive sort algorithms. Computer scientists try to find the best sort algorithm, and so the quick sort's the best sort. unless the cardinality of the data or the histogram distribution of values and the skew in the data is a certain way, in which case the insert sort is better or the shell sort is better. And so understanding how these things behave is very interesting, and these guys figured all this stuff out 100 years ago. What this stuff teaches us, just looking at sort of books and libraries and all these other things, is that information does require organizing principles, and at first, when you just have 50 or 60 of something, you can dump them in. This is very much like using Splunk for data analysis. I have one big deep clickstream data set, dump it in, it's great. Throw in my customer data, my product data, my sales data, my costs, and suddenly you have to build big, messy systems that can't navigate anything because you have essentially one big wide search index and you can't join data. And joining data is one of those things that turns out to be really important. And that means categorizing data into different chunks, having a global schema that just tells you where to find the different data sets. Second thing is differences in scale require different principles. It was easy enough to shelve books when we had 200 million of them worldwide. It was very hard to shelve books when 200 million were produced every few months. And so it's just like today's technology revolution, where the ingest rates of data that we have coming out of the systems we have today have outstripped anything that has been produced. It's multiple orders of magnitude shift of data rates. Third thing is that in the adoption cycle of information, there's a point where people stop paying attention to the creation of the thing and start paying attention to the consumption of it. It's what happened with libraries. It's what happened with a lot of this other technology. First, you pay attention to how can I capture the transactions, shelve the books, and do other stuff. And then later, you think about how can I get the stuff back out? How can I use it? If you can't solve the capture problem, there's not much reason to pay attention to solving the query problem. And that's how a lot of database technologies have evolved. So when you think of analogies, one of the ways to think about data and databases is that, data is to database as books are to a library, right? The data in a data structure in a program is a structure that has a schema. Now, when I say schema, I don't mean a relational schema. I mean a schema in the sense of organizing structure. So a structure in a Java program or an object or a C struct, these are all structures. A book has a very rigid structure, and the data fits into that thing. The library is the collection, and there's a big difference between dealing with eaches, individual items, and collections that has been lost on the industry for a long time, and many programmers don't realize why set-oriented models are important. And they're coming back in a big way. And the other thing is that there's a point where the printed became more important than the thing that produced it, the printer. Lots of history focuses on printing presses. Very little history focuses on how people organized and managed the books that came out of them. The same is true of the data markets. And so it's a good analogy in thinking about how one manages it, because there's two sets of things here: the production of stuff at scale and the consumption of this stuff at scale. And so one of the things you need to think about is that when you write an application, it might be Pinterest, huge scale application. It might be a little thing for your department. When you build a web app, when you build a mobile app, anything, it's going to produce data that is useful for that application. The other thing that comes out of it, though, is that other people will find that data useful. There is a life cycle to data that extends well beyond your program. And so when an order, for example, comes in, customer service needs access to that, but they do things to it as well. If you build a nice Mongo data store to take orders, you may discover that the model of access path and the nesting relationships you constructed in that nested hierarchical model do not map to what customer service needs. So what do? They force you to redo your physical model, or they siphon the data out. And historically, what we've done for scale reasons and other reasons is to just keep moving data from system to system and pass data around in the organization until it looks like this. I've done a lot of IT work, and I'm always looking at system context diagrams that show data flows of data sets that look like this big rat's nest here. Now, the thing, I love the Douglas Adams quote, "In an infinite universe, the one thing sentient life cannot afford to have is a sense of proportion," because when you start looking at this, you feel like it's hopeless. But it isn't hopeless. It's just that sometimes you have to think beyond how your program produces data to how it gets used downstream. As developers, and I was a developer for a long time, we think about what's inside the box, and then if somebody else uses our data, that's their problem, not mine. The thing is that code lives longer, or that data lives longer than your code. Data always lives longer than code, just like books outlasted the printers that produced them. And when you look at other kinds of supply chains, I just showed you one company's system diagram, and it wasn't even a big company. This is the multi-industry data flow for cheese production in one country. And so it's a very abstract one, but all this stuff up here is data flows going back and forth between all of the companies down here. And so there are levels of composition of data that go beyond the system, the process, and the organization to this sort of very large perspective. And that's the context within which this one little application over here runs, but the data that it produces might go all over the place. And so you have to think about how data is produced, what its lineage is, what its structure is, so that other people can consume it, and other people, other systems, other processes. And that gets me to a point about design. So I'm going to take a quick sidetrack here, because really what I'm trying to get at with a lot of the things that I talk about is better ways of designing systems. And one of the things that we have a lot of is technical debt. Now, technical debt is basically just what happens when you make a decision with a trade-off, right? I'm going to do this now because I have to ship in 3 weeks, and I'll fix it in the next release. So you've taken on a debt there, intentionally taken on that debt. Other times, you didn't know. You missed a requirement. You made a mistake. There was a bug. You didn't understand. The Pinterest talk was great for talking about, we tried this, and that worked for 6 weeks, and then we had to throw it out and get a whole new different platform in, and then we tried that, and that, it reminds me of the Monty Python episode with the swamp. I built a castle in the swamp. People said I was crazy. I did it anyway. It sank into the swamp. So I built a second castle. That one also sank into the swamp. So I built a third castle. That one burned down, fell over, and then sank into the swamp. But the fourth one finally stood. We can avoid some of those fourth one finally stood if we understand we're building in a swamp and what the nature of building in a swamp is. And working with data is often like that. Now, that said, a lot of times we like to blame our tools. Oracle doesn't scale, or relational databases don't scale, or sharding sucks. It is the poor carpenter who blames his tools, except that sometimes the tools really do suck. So think about technical debt in terms of the kinds of things you accrue in your software portfolio from a short-term and a long-term perspective. And what you'll find is the short-term stuff is going to be mostly about your application code up here. So, you can do a lot up there. Infrastructure, architecture, and design are a different nature of problem. And one of the things that I would argue is that a lot of iterative design, which comes out of agile development and DevOps approaches, is great for turning features fast and truly terrible for building core infrastructure. You don't build a city by not planning it and just letting a shantytown grow up. You build a city by creating zoning and building infrastructure and roads and water and electric and sewer plants that support the things above it without constraining them too much. And the balance is not having over-heavy infrastructure, which we have had, I would argue, for a long time, and not enough freedom on the front end. But if you go the other direction, it's just as big of a mess. And so the kinds of short-term debts you take on and the long-term debts you take on will manifest later, and that's what leads to big failures sometimes. Now, when you think about the decisions that led to these things, up here, short-term, intentional. I meant to do that. We're not going to put this feature in, or we're going to do it this way, and then we'll fix it in the next release. Long-term, it's more like design choices. We're going to design it this way. It will constrain what we can do, and we may have to fix it 2 years from now. Versus the unintentional things, the flaws. And how you address them methodologically. There's a lot of stuff at this conference about, in particular, agile and DevOps things up here to solve these types of problems versus, redesign. And over in here in the unintentional box, experience and education is typically the only way we have of getting out of that. And what I'd like to see more of is moving out of this box and shoving important infrastructure decisions, which in my book tend to be hardware topologies, network topologies, models of use, and persistence layers into an intentional box where we understand the trade-offs that we are making. The question is, how did we get into this mess in the first place? So I'm going to throw some history at you. This is sort of the database industry history. And what we've got here is, starting back in the 1960s, multi-value data stores. In a multi-value data store, you could have variable structures of records, just like we have in Mongo or Cassandra or HBase. So these models have existed for a long time. We had hierarchical databases, which let you build out a hierarchy, which is very much like for example, a document model database where you have a customer and then you wrap the orders inside the customer, or the classic example of Mongo's, blogs and comments model. And you make a trade-off there, and you make a trade-off here, and it's exactly the same trade-off. So if you read design literature from the 1970s for IMS, you too can be a good Mongo designer. Because the principles that operate behind these pre-relational databases are all the same. My career started with record management systems, which is basically just spitting structs onto a file system in records. And you had 4 primitives for navigation. Apart from opening and closing, you had the first, the last, previous, and next. There was no index, there was no B tree, there was no key to look up. We had to layer those things on. And the databases that came about in this era, like Database or IMS, gave us some things like recoverability and ACID transactions, and moved us out of this record-oriented model where every navigation you had to do in your code. But I see Java people still do this today. They write a query against a relational database, pull it into memory, and then do the join in memory, which is an iteration, building iterators. And that's not really a good idea. It's not a good idea for a key reason. So I don't know how many of you have seen Conan the Barbarian, right, a classic cult film. What is best in life? Well, according to Larry Ellison, what is best in life is to crush the vendors, to see them driven before you and hear the lamentation of the salespeople. And that's driven the computer industry for a long time, but I would say wrong. It's loose coupling, reusability, and scalability. And that's what databases, pre-relational databases, gave us. They gave us loose coupling. Instead of me writing records into a file, I have this schema descriptor, which just says this is what the data looks like. Now, I could have written something else into there, but that's what I was supposed to put in there. And so somebody else can come along who wants to use my code, because our key problem in those days was reusability when I wrote a file up. And so now I've got this idea of loose coupling where the schema is separated from the physical storage, which means now some other system can handle optimized navigation of data on disk or cached in memory. My program simply has to call the API to get it. It gave us schemas, which gave us reusability of code, multiple applications writing against the same data set. It also gave us reusability in the sense of data portability. Because back then, everything had to be written through libraries. Everything had to be done all these different ways. And so there was no portability of data from one place to another, because you had to rewrite all of the data in a different program, different language binding. Third thing was scalability. Once I handed over a whole set of tasks around I/O to a database, it could start to manage concurrency far better than individual programs reading and writing data. And so we got some great things back then, which are very similar to things we have today. And what we've been pushing today is relational databases suck because they're too rigid. Therefore, we need schema flexibility. Well, we had schema flexibility. Relational database implementations today traded it off, and they're starting to build it back in again. But what the trade-offs are is really these right here. Global validation versus local validation. Right? The context of your program defines the rules for what proper data is that goes in and out, versus everybody must conform to this rule. Schema is an assertion about data, that the data looks this way, and if you have typed schemas, then that they fit into those types. And so global schema rules, like a relational database has, or like IMS had, are very strict. These types and these columns, if you try to put characters into a numeric column, it's going to kick it out. If you do that in a document database, it doesn't do that. If you do that in HBase, it doesn't do that unless you enforced these rules. So you have the ability now to decide when that's important, and I think that's a really good thing. You have rules on read versus write, and that's really a useful thing too because, for example, in systems I've built that take telemetry data, like game telemetry data coming in at a constant rate over the network, the games and the firmware and the devices and 100 other things change every week, which means the record structure varies week by week. It's the same data, maybe it's been reordered, maybe something new has been added. If I have to stop operations, alter a table, reload that table, recreate that table, change code in order to write that data into that table, I lose data. And that's exactly what happened to me. We switched to things that just did log ingest and variable record structures. I don't have that problem anymore, but I've shifted my workload. I've made it easy to ingest data very, very fast and more or less know what data is there. For example, if you use HBase, you know what's in there. You've got variable structures. Your problem is if you want to read out specific sets of data, you pay the price on the outbound side because your data typing, your efficient storage, and everything else are not there because they weren't done at ingest. So you do all that work on the other side. But we have enough CPU and we have enough I/O bandwidth in a parallel system that typically we can eat those costs on the outbound side, which means that now you have a choice. Match the data to the table, relational models, or match the table to the data, predicate schemas. And so you do have problems, though, that sometimes you don't recognize. And one of those problems is inflexibility. What you think of as flexibility, like MongoDB, a friend of mine is a statistician at Amazon. He deals with lots of data. They built a new system for a new feature in Amazon. The developers came to him and said, hey, we're going to try out Mongo for this. Do you mind? And he said, no. Can you give me this data? And he said, yes. I can give you that. I can build this in Mongo. It'll be great. So they went off. They built the system. They got it back. He got this stuff. They did some statistical analysis. And then he was looking at some of these things. And he said, this is great. I need this information over here. Well, Mongo, like IMS and things before it, has a model that requires you to physically couple your data structure with what's written on disk. There's no loose schema model here that lets you say, like a relational database, throw a new table out here. You have no joins in most of these NoSQL databases, which means if you need flexible out on your data, you have to rewrite the schema. So they went away for 3 weeks. They recreated, dumped, and reloaded the database. He did some more analysis. A couple weeks later, he needed some different data. And again, 3 weeks to make a schema change. And this time they did it smart instead of dumb. They didn't dump and reload. They did a lazy rewrite pattern against it. So, you read the old data in and you write it out in the new one. And over a 3-week period, it churned enough data that he could do his analysis. But after that, they said, we're not going to use this anymore because every time we eat that, and the reason is back to that simple principle from the early days, decoupling. If you can decouple the logical model of your data from the physical model of your data, whether it is relational or not, you win something. And that gets us into some of these things like the CAP theorem, which is the big driver for a lot of these NoSQL databases, which was here's how to try and scale by eliminating things like transaction coordination, which is a key bottleneck in data systems. Anytime two things have to synchronize, you serialize. And when you serialize a point, you limit parallelization, which means you limit scalability. And so most systems that you look at are down here on, say, the AP-CP axis. And what this is consistency, partition tolerance, and availability, right? Consistency, if you write data and I read data, it's consistent. I'm not reading halfway in-flight committed transactions. If you're looking at availability, it's that the clients can actually get access to the data. And if you lose part of your system, for example, lose a disk or lose a node, the system will hang if it's a CA system, which is modern relational databases. Whereas if you are eventually consistent, like Cassandra, Mongo, whatever, you choose something on these axes, and what you give up is consistency. And that consistency trade-off is the thing that most of these databases made, because most web apps don't need ACID transactions. They don't need to worry about bank balances. I might lose a registration for a newsletter. Who cares? The upload from your mobile going to Pinterest or Instagram, if it fails and you're looking, you can re-upload. It's not a big deal. Whereas if that were a 10Q filing for the stock exchange and the filing didn't go through, you're in trouble. So there's a big difference between when you do and don't need this. Now, what are you trading off? Because the trade-offs are the key thing, because you're going to inherit technical debt if you choose the wrong thing. And so this is what a relational database does for you, right? Storage management, data access, data navigation, query optimization, transactions consistency, and of course a standardized layer that's universal on top. When we started out, I was doing record management systems. By the time I moved into the few years into my career, we had databases that did data navigation, handled joins for us, dealt with the physical data access, left me to deal with the higher level. When relational came along, we got all this stuff. And so a relational database does this. If you choose not to go that route, this becomes your job. And that's important to know. A lot of times people just assume, oh, I've got good enough transactions, because if my database is consistent within 10 milliseconds, there's no problem, right? Wrong. Google transaction malleability and look at the Bitcoin repository failures, and what you discover is that they built things with non-ACID semantics for a financial system that had hundreds of millions of dollars in it. And that led you into problems where I could do several different attacks. This particular problem leads to basically the equivalent of non-durable reads or non-isolation of transactions, which is a simple way of saying it's wrong. And so you can pull out more data or pull out more money than is in. There's other attacks that you can use against non-ACID systems, like the difference between cache latency and physical I/O. If you send your requests fast enough, you can withdraw essentially from your bank account twice as much money as you have in your bank account. That's why we have ACID transactions. And this argument's been going on for a few years now, and Google last year wrote a paper for the F1 database, which I've referenced here, and I just have a few quotes from it, which essentially say, this is you and your code. And so over time, the edge cases to deal with eventual consistency when you need consistency outweigh the costs of performance that you take over here from not having it. And so we're going back. The F1 database is a fully transaction compliant, globally distributed ACID database. And a number of new databases on the market are also going this way, because it turns out that the relational model is useful enough, and some of these things are useful enough, that if you can relax them in certain contexts, but still maintain the rest of the model, you're better off than if you threw it out and started from scratch, which is where the industry is today. And that kind of brings me sort of back to 1985, when we looked at the performance of these systems. Relational was standardized, SQL became a standard in 1986. And that was really the opening gates for things. And at that time, a hierarchical database gave you far better performance, 3 times the performance at a whopping, 30 transactions per second. Or 100 transactions per second, 30 IOPS per disk. Right? Think about that today. We're doing 2 million IOPS. But 25 years later, one single SQL Server database could do that. And the interesting thing is why it could do it. Right? Part of why it could do it was the things that relational models gave you. And one of those was joins. I no longer had to navigate through data. Fixed path navigation, that's transaction processing. Every transaction is like every other transaction. You know the I/O path, you know the code path, you know everything that will happen. It's so predictable that you can just build that. Queries are a different story, because queries don't have to be fixed. They can vary, because it's just this set of data to that set of data. And the interesting thing, of course, is you throw out queries, and the first thing people realize is there's more than one kind of join. And then you think about things like, I can't get MySQL to scale, therefore I'm going NoSQL. or I can't get relational to scale, so we're going to do something totally different when the problem is probably something else. And when you think about the gift in 1985, 86, actually the heritages in System R, which came earlier, is at the core, is declarative language. A declarative language, as opposed to a procedural or imperative language, lets the machine figure it out for you. In the same way a compiler can optimize the loops in your code, a database can optimize the path of I/O through the engine to get the results that you want. They're not perfect any more than compilers are perfect or JVMs are perfect, but they get you something that you didn't have before. The second thing is cost-based optimizer. If you know that disk costs this much, and I/O here is this much, and network transit costs this much, and a memory access is this much, you can choose the best path. And this is important, and it's the only way you can do this is if you separate logical schema from physical schema, and you don't lock the storage model and couple it tightly to the representational model of the data. And what this optimizer does is it says, here's all of these things that I can do. The way that it gets that is that the declarative language, which happens to be SQL in this case, the operators are commutative, associative, and distributive, which means the optimizer can change the order of them. Why is this important? Well, imagine that you have 10 million customers, 100 million sessions, and a couple billion clicks. You can join those things based on the least populated table or the most populated table. If you choose the wrong one, you burn a lot of extra time and you waste a lot of resources, which translates into wasted time in your code, which translates to latency in your application. And the optimizer tries to fix this. Now, how hard can this be? Well, this is a simple thing. Selecting 3-table join. Customers, 2 orders, 2 products. I just want to see the customers and orders that, say, contain a particular product. There are 9 logical plans to this, 9 ways of ordering the tables, A, B, C, C, A, B, and doing the joins. Now, the physical layer joins, hash join, merge join, nested join. Now, most of us programmers would say, oh, just slap it in a hash and do that. Not efficient under certain levels of cardinality. Nested lookup would be better, or a merge would be better if they're already sorted. So the possibilities, the combinatorial explosion for this simple query is 324 possible physical join plans. Now, I want you to think about this when you are writing a query against a Cassandra database, because there is no join there. So if you have to do a join, how does it happen? You write a query here, you write a query here, you bring the tables together, and then you do it in your own code. Did you think about every single possible one of these joins that you could do to order your operators correctly to get the optimal result? I really seriously doubt it. If you wrote a pig script in Hadoop, did you do this? Very unlikely, because that's a lot of work. And it varies with the cardinality, with the distribution of values and the skew in your data. And so if you know those things, you'll choose one plan over another. A query plan is dynamic. A program is static and written by you. And so, what's the solution? Well, the obvious Hadoop solution, throw nodes at the problem. Just add hardware. But of course, I love this quote about the software industry and basically how software simply eats hardware for lunch, because that is what happens. And since your database is web scale, don't worry about it. Well, when you write code to do this, you have one path, and typically you'll write it with something like this, iterators inside, and you'll iterate over this. Declarative languages make this a heck of a lot easier. And this will not run in parallel. Short story, 1994, we have just sold a $1.6 million symmetric multiprocessing server with a whopping 32 cores in it, which, in the 1990s was just amazing. Developer came to me with a bunch of code he had written, procedural imperative, a lot of iterators, opened up cursors, did things like this. He wrote it really tightly. It was actually very nicely written code. And he told me, my laptop is faster than the 32-core server. And he was convinced of this fact. And I said, how can you be, sure of this? And he shows me the numbers and he shows me the graphs. And I looked at his code and I said, you do realize that all of this fits in the processor cache. And it's single-threaded. And he said, yes, but I round robin the data and I spray it out to each of the 32 processors. And so my reader reads this and spreads it out. And so I'm doing, and I can get better scale than your system. So why would I do this? And I rewrote his code, which was probably about 8 or 9 pages, into a series of 3 pages of SQL statements that just happened one after another. And of course, I lit up all 32 cores on that system because the stat he had not looked at when he ran it on his laptop was how many threads he had running on the database server. Why didn't he have all the threads lit up? Because he wrote serialized code. The problem is that no amount of hardware solves serialized code, and it's very hard to write parallel code. And so, yes, things like MapReduce give you shuffle operators and other things, but you can still write very sloppy code. It's very hard to do. A more realistic example, a query like this, which is what most, say, BI query tools generate out the back end, 22 million possibilities. That's a lot of choices, and you have to come up with the optimal answer for that in a few milliseconds. Declarative cost-based optimizers, just-in-time compilers, query compilers, things like that solve these problems. I'm not saying use SQL to solve data processing problems. Use declarative languages. Datalog is perfectly acceptable alternative to SQL, and it's a logic language. I don't really like logic languages. I prefer functional languages, but that's what it is. Key point about just add hardware. And if you're interested in this side of things, I've stripped all the database performance stuff out of this talk. This is Amdahl's law, right? This blue line, that represents adding processors and getting better performance, linear scale. If I add 4 processors, it's 400% faster. If I add 8 processors, it's 800% faster. With 10% of your code being serial, 10% having to do some sort of rendezvous or create a lock and block something. 10% having to do a boundary synchronization, basically a map reduce, so you can do the next map reduce. 10% overhead leads to this curve. What does this mean? It means that right here, you stop adding processors or you stop adding nodes. Why? Well, my 4th processor gives me the equivalent of 3 processors. My 5th node gets me 1/2 of a node. Real life example of this was in 1993. I ran TPC benchmarks, and I was running a benchmark on a 4 processor HP server. It cost $2 million. Each proc board cost about $250,000. In the HP server, they had 15% overhead. At 15% overhead, the simple calculation of Amdahl's law, which is not the best one, by the way, that 4th processor got me net zero. It got me about 10% of a processor. $250,000 buys me 10% improvement. And everything that you're doing is going to have some level of parallel inefficiency. So it's important that you look at your data, you look at your algorithms and your code, and you try and figure out where useful parallelism ends. Because throwing another 100 nodes of Hadoop cluster or Cassandra cluster or Teradata at something won't solve the problem if the algorithm or the query can't take use of it efficiently. And so if you want to know more about this, the high-frequency trading talk that's this afternoon that Martin Thomas does is really good because he gets into a lot of the theoretical constructs, but he's talking about it from the perspective of messaging and queuing systems. And as it turns out, it's exactly the same in principle. So I want to give you a real-life example in case you don't believe me. eBay, 6 petabyte data warehouse running in a standard Teradata, 20 petabyte compressed, obviously, Hadoop cluster, and then this thing called Singularity, which is a Teradata appliance model database. It's got the really big, slow disks in it that has 40 petabytes in it. Now, I've had the opportunity to actually run a couple of queries against this thing, and a trillion row table with about a 40 to 50 billion row return set filter on this takes 30 seconds. This is the important thing, though. That Amdahl's law is about resource efficiency and parallel efficiency. Sloppy code and just add nodes is not efficient. We learned this with symmetric multiprocessors, multi-core chips, back in the 90s, even in the 80s. If your code or your system that underlies your code is not efficient, that is, it wastes resources, say in doing type conversions every time you read data as opposed to doing the type conversion once before you write the data, slows things down. So this first graph right here, How much do things cost? So normalized costs, Hadoop, damn cheap, right? So that's a per unit cost of 1, right? The Teradata appliance and the big expensive Teradata nodes, ridiculously costly, like 30x what Hadoop costs. But look at this one then. How many units are consumed? Now what we're talking about is the kind of things we do a lot of. Sorts, aggregates, counts, groupings, select these things, group them in this way, aggregate these numbers and give me the results. Big, ugly, bulk moving parallel problems. And the data warehouse is extraordinarily efficient. This thing not quite as good, and of course that thing horribly inefficient. Why? Because of things like read 64 megabytes in to pull 4 things out of it. The inefficiencies at scale bite you in the butt. And so when you look at what does the units consumed crossed with the cost look like normalized, well, that big expensive multi-million-dollar Teradata that has 6 petabytes in it costs the same as your Hadoop cluster, and yet equivalent. This thing right here, which is modified for bulk data operations and bulk data parallel, that's about a third the cost of your Hadoop cluster for the same set of operations. This blows a hole in the argument that just add hardware is the right model to go in the big data world. But for which operations, right? For parallel, count, sort, aggregate operations. If I was doing calculations and bulk calculations that didn't stream through that but iterated, this would be the better option probably. And so you have to begin to understand what your workloads are like, because if you don't, you'll make the wrong mistake, because we're in a multi-engine world now. And so, yes, this thing is great for these problems, but if I have a different set of problems, I've got a different set of solutions. So workloads are key. And there are 3 kinds of workloads. I started off talking about application workloads and writing data and reading data and ACID transactions and consistency. That's one set of systems. Brief aside I had with the guy talking about Pinterest is that he said, I needed ACID transactions. Like, you're Pinterest. People upload pictures. Why would you need this? And he said, we get DMCA takedown notices. If you forget to file a DMC takedown notice that somebody has sent you, you've just broken the law and the lawyers come after you. So even simple websites that seem not to need things like ACID transactions, in certain cases do. So what do? Well, you could have a system that records that stuff in ACID transactions while your web serving loads that can lose stuff and it doesn't matter or can be inconsistent. You can write two different services, or you can go with what they did, which sharded MySQL. But that's an operational system. Analytic systems, which is what I spend most of my time working on, big query systems, big analysis systems, and scientific computational systems, big data processing, computationally intensive things. They're all very different. The natures are different. So how are they different? These are the key things. I'm not going to go over all of this. You can download the slides if you want to look at it in detail. But basically, distributed commits, problems with consistency, making sure that I can't take more money out of the system than you put into the system. Scan-based selective things. And a key aspect of these systems and what they're good at is whether the selectivity and retrieval are low or high. Selectivity is how much data do you actually filter out down here. Retrieval, how much data do you pull back, whether it's into your process or to a client over the network. Analytic computations read 100% of the data, process 100% of the data, and typically put either a small set out or an entire set out. These things usually summarize. They don't return lists, they return aggregates. That's why BI databases actually have optimized so well, and that's why that Singularity system can do that where Hadoop can't. This sort of stuff, now you're into a world where if you need ACID, you need consistency, you go one way. If you don't, you have a whole new range of options that you didn't have before. And so you need to think about those workloads and think about, performance over size versus performance over complexity. If you're interested in that, unfortunately, you just missed a fantastic talk by Cliff from Hex Data, but you can watch the video because it's being recorded. And that's all about, very important things here. For example, in databases, you would think disks are the bottleneck. I/O channels are the bottleneck. They're slow and I'm getting data into memory. In-memory solves all problems, which is what SAP would tell you with HANA. Doesn't work that way. If your algorithm is not smart about how it moves data through the processor pipeline, you spend upwards in the relational world of 60% of your time on level 1, level 2 cache stalls. You wouldn't think about this, but if that's where you're wasting all of your time, more resources won't help you. More memory might help you, but unlikely, because the problem is that your memory is not feeding your cache fast enough. It should be able to do that. Why can't it do that? Because the way you move the data into memory and process it is not optimized for that. Pushing that into engine solves that problem. That's one of the things Hex Data does, Dynamic does, Vertica does. And so, when you think about these problems, we've kind of come as an industry full circle from the early era of we have no SQL, which is where I started, to no, you really need this stuff, to the 2000s when everybody said, no, SQL's bad. Memcached. Memcached will solve all problems. They'll just use key value stores for everything, too. Mongo and Cassandra and everybody's saying we don't need no stinking SQL, and then they all added SQL-like languages back in, but they called them HQL or CQL or whatever. And now we're back with, the Google paper and other things, and post-relational systems like Metanautics or Snowflake, which are extended relational. They have kept that model and the declarative, added new operators, and made them better and relaxed some of the constraints. So where we are is there's no such thing as a free lunch. You're always making trade-off decisions, and you will inherit technical debt. And you have to think about the data infrastructure because it's so hard to change once you've built an application on top of it. Know your trade-offs up front and understand some of the wheres and whys of these things. And avoid the unintended consequences. You installed Mongo, and then you didn't realize that the tight coupling of data structure and schema to physical storage led to a whole new set of problems. This is my favorite example. I use it a lot for unintended consequences, which is that back in the 1950s, atomic power was all the rage. And atomic power was going to solve every problem society had, just like NoSQL today. And so radium, being such an easily available thing, we could paint it on watch dials, and radium is radioactive, so we'll put it in chewing gum to give you extra energy. Women's makeup had radium in it for that extra healthy glow. And my favorite example of all, the only one that works, the radium-laced prophylactic. So condoms with radium that actually would prevent, not just the current pregnancy, but every possible future pregnancy. Those are the unintended consequences that you can inherit when you make the wrong technical implementation decision. Now, I'm sad to say there's no one answer. Cloudera and Hortonworks would love it if you just bought Hadoop and threw everything else out, but that's not going to work. Oracle would love it if you just bought an Exo whatever and paid them $8 billion, but that's not going to work. We're back to best of breed architectures. For a whole generation, my generation, we thought the relational database was the answer, but it turns out that there are multiple workloads with different answers. And that's the world that we're getting back to. And so, don't make these mistakes that some of us made that we had to unlearn, because I spent the past 7 years unlearning a lot of stuff, which is that you really have to say, what is the problem for which this technology is the answer, number one, and number two, more important one, what's my goal, and how does that translate into the capabilities that I need, and how does that map onto those technologies? And finally, there are no best practices right now in this world. There are some good practices, but mostly best practices come from survival bias. And survival bias is the people who made it through the minefield. And it's great if you can follow them through the minefield and take 3 steps to the right and 2 steps forward and 1 step left. But every company is different. Every engineering team is different. You're not starting from the same place that guy started from, which means that if you follow his exact pattern of steps, you're likely to step on a mine. And that's what we're learning in the emerging tech world now. And so really what you should focus on is a lot of the worst failures. What was the real story of why Mt. Gox failed? We may never know, but they blame it on transaction malleability. We know what that is, and we knew what it was in 1972. So there are solutions out there. Look for those failures and study the pattern of those things, and you'll learn a lot. And so that's just the summary of the course. And with that, I'm finished, and you guys are all free for lunch. So thank you very much for coming.